Welcome to the Explainer. Today, we're unpacking one of the absolute most fundamental principles in all of fluid mechanics. Whether you're a civil engineering student staring down a really tough hydraulics exam, or you're a working professional designing massive urban water networks, what we're about to cover is literally the bedrock of how we understand fluids in motion.
Think about this for a second. If you've ever stood out in your backyard and just put your thumb over the end of a flowing garden hose to make the water spray further across the lawn, well, you've instinctively applied advanced fluid mechanics. You actually manipulated a fundamental law of the physical universe, which is the unbreakable rule that fluid mass can neither be magically created out of thin air, nor can it be mysteriously destroyed. I mean, the water has to go somewhere, right? So today, we're going to take that totally intuitive physical reality and translate it into the beautiful, structured mathematics that governs 1, 2, and 3-dimensional fluid flows.
So here's our roadmap. We're going to logically build this up. 1. The principle of mass conservation. 2. One-dimensional pipe flow. 3. Two-dimensional fluid motion. 4. Deriving the 3D equation. 5. Compressibility to simplify the math. And finally, 6. Summary and takeaways.
Section 1. The principle of mass conservation, the unbreakable rule.
Okay, let's dive right into this. The entire continuity equation is basically just a mathematical statement of the principle of conservation of mass. Now, in fluid mechanics, we typically use what's called the Eulerian approach to describe this. So instead of trying to track every single microscopic drop of water as it zips through space, we define a fixed region, or what we call a control volume. Just imagine an invisible, perfectly rigid box suspended in a flowing river. Because fluid can't just vanish or suddenly appear, any increase in the fluid mass inside that box absolutely must be exactly equal to the mass flowing into it minus the mass flowing out of it. It's a perfect balance.
So picturing this conceptually, you have this fixed region. Mass is entering on one side and leaving on the other. Now, if the flow is steady, meaning the conditions just aren't changing over time, then the rate of increase inside that region is exactly 0. What goes in perfectly matches what comes out. It really is just an incredibly simple, beautiful accounting system for physics.
Moving on to Section 2, one-dimensional pipe flow, the stream-tube.
To really visualize flow in just one dimension, consider a single stream tube. In true one-dimensional flow, the fluid's velocity only varies in the direction of the flow itself. If we assume the velocity is totally uniform across any cross-section, we completely ignore the y or z axes. They just don't matter here. And a larger flow passage? Well, that's really just a bundle of these much smaller stream tubes all packed tightly together.
And that brings us to the absolute most famous and practically useful form of the continuity equation for 1D incompressible flow. Q equals A1 times V1, which equals A2 times V2. Here, Q is your discharge, or your total volume flow rate. A is your cross-sectional area, and V is your velocity. Because the density of something like water basically doesn't change, this massive balancing act just becomes a super simple geometry problem. If your pipe gets narrower, meaning area 2 is smaller than area 1, the velocity, V2, mathematically has to increase to push that exact same amount of fluid through. And boom, that is exactly what happens when you put your thumb over that garden hose.
Section 3. Two-dimensional fluid motion. Adding the y-axis.
Now, in real-world civil engineering problems, flow often spreads out, right? Think of water flowing over a really wide spillway on a dam. In two-dimensional flow, the velocity actually has components in two coordinate directions. We call the velocity in the x direction u and the velocity in the y direction v. So the continuity equation has to evolve to account for this. We're now looking at partial derivatives. It's the change in u with respect to x plus the change in v with respect to y equaling 0. All this shows us is that a change of velocity in one direction is perfectly offset by a change in the other, which keeps all our mass perfectly balanced.
Section 4. Deriving the 3D equation, the mathematical heartbeat.
All right, now we are ready for the ultimate mathematical heartbeat of this entire concept. Picture an elementary rectangular fluid volume, basically a tiny 3D box. We are introducing the z-axis here, with its corresponding velocity component w. Now think about the faces of this box. Our goal is to measure the precise mass flux, meaning the actual mass passing through per unit of time. We want to know exactly what's entering one face and leaving the opposite face across all 3 dimensions of this tiny box.
The calculus happening here is genuinely a beautiful step-by-step logic puzzle. First, we take the mass entering the left face and subtract the mass leaving the right face along the x-axis. But because the velocity and density might change just slightly as we move across the box, we use a partial derivative to express that tiny, tiny difference. Second, we literally just repeat that exact same process for the y-axis top and bottom faces and the z-axis front and back faces. Finally, we add all those net changes together, and remember, according to our unbreakable rule from earlier, all of that net flux must exactly equal the total rate of mass increase inside the volume itself over time.
So when we take those steps and essentially divide out the volume of our little box to look at a single mathematical point in space, we get this, the general 3D continuity equation in Cartesian coordinates. It's the change in density over time plus the spatial gradients of density times velocity across the x, y, and z directions, all equaling 0. This magnificent equation is universally applicable. It absolutely works whether the flow is steady or unsteady, whether it's uniform or non-uniform, and whether the fluid is highly compressible like air or totally incompressible like water.
Section 5. Compressibility. Simplifying the math.
Here's where it gets really good. When we're dealing with liquids under normal conditions, they are incompressible. This means their density, which we represent with the Greek letter rho, just doesn't change with time or space. It is a constant. And because it's a constant, we can essentially factor it right out of the equation. Furthermore, if the flow is also steady, that very first term concerning time completely vanishes. What you are left with is just stunningly elegant. The partial derivative of u with respect to x plus v with respect to y plus w with respect to z equals 0. It's just pure velocity components keeping the physical world perfectly balanced.
Section 6. Summary and takeaways. The big picture.
Let's wrap this up. First, never forget the foundational premise. Mass simply cannot be created or destroyed. What flows into a space must either flow out or be stored. Second, for simple pipes, 1D flow gives us that highly reliable area times velocity relationship. Third, as complexity increases to 3 dimensions, we rely entirely on tracking the mass flux across the x, y, and z axes of a control volume. And lastly, for most of the fluids you'll ever design infrastructure for, constant density strips away the hardest parts of the math, leaving us with a clean, workable relationship of varying velocities.
The math behind our physical world is rigorous, yes, but it is incredibly consistent. I highly recommend you open up your textbook, grab some paper, and actually try deriving the 2D equation on your own from scratch. Mastering this early on is going to make jumping into the momentum equations an absolute breeze later. But before you go, ask yourself this. What happens to this perfect mathematical balance when the fluid becomes fully turbulent, just spinning with unpredictable chaos? Well, that is where the true challenges of fluid mechanics begin. Thanks for joining me on this explainer, and I'll see you next time.